multiples, so that if somebody is interested, they can go deeper in this area. It's a very hot topic. So as we discussed earlier, there are many applications of multiples technique that we already discussed. Okay, these applications we have already discussed. Then what are basically, they are rectifiers fed by three-phase sources. These things, on AC side there is a problem, DC side there is a problem with rectifiers. So these things we have already discussed, and we were talking about two separate 6-pulse converters. Okay, and dy1, dd0 we have already discussed how 30-degree phase shift gives, instead of 6 pulse we have a 12 pulse. So this we have already discussed, like 5th and 7th harmonic is eliminated. So since it is a 12 pulse, so 11th and 13th harmonic will be there. So as you can see here, 11th harmonic is there, but 5th and 7th harmonics are cancelled. But if we have anyway, so here you can see there is a phase shifting between DDO transformer, 0-degree phase shift, dy1 has 30-degree phase shift. So that's why there is a phase shifting here and here in instantaneous voltages. So the problem of circulating current, so that is why we were using interphase transformers. This we have already discussed. I think I have some problem, my slides are not moving. Yeah, okay. How to escape? Why it is frozen? It is going for, ये आगे बढ़ता जा रहा है, पीछे नहीं जा रही स्लाइड्स, एस्केप भी नहीं कर रहा है. कुछ बात नहीं, में हम आगे बढ़ते हैं. ओके, अच्छा इसे रीसेट करना पड़ेगा.
हो जाता है सब चार्ज नहीं है.
चार्ज, हाँ ये चार्जर है इसका.
सर हो जाएगा.
अच्छा, talking about in general minimum phase shift required for cancellation of current harmonics in converters with 6-pulse waveform, 6 pulse. So phi is the minimum phase shift. Okay, so 60 divided by n, n is the number of 6-pulse converters. So if you have two 6-pulse converters, so basically 12 pulses and 60 divided by 2, right? This is what we were discussing, because there are two converters. So 30-degree phase shift. So if you are having two converters, like we were having dy1 and dd0, two converters were there. So why we were giving 30-degree phase shift? Because this is the requirement, minimum phase shift is 30-degree phase shift required. So that's why we were giving 30-degree phase shift to cancel 5th and 7th harmonic, right? So this was the advantage of giving the phase shift. So this is what we were doing, that if we have two converters, two 6-pulse converters, so 30-degree phase shift. If we have 3 6-pulse converters, then you see 18 pulses. 18 pulses means minimum you will have 17, right? So below 17, all the harmonics are already removed. If you have 3 6 pulse converters, and how much should be the minimum phase shift? 60 divided by 3, because we are talking about 3, so it means 20-degree phase shift. So if you are having 3 converters, 3 6 pulse converters, so minimum phase shift would be 20 degree to get 18 pulses, so that below 17th all the harmonics are already removed. So this is the advantage of giving the phase shift between the converters, right? So n is equal to 4, so 24, 6 multiplied by 4, 24 pulses, and 60 divided by 4, so 15 degree. So this is how you can calculate for all these things, right? This is also we have already discussed. So if we have one converter, 6 pulse converter, so this is the equation. So you will have 5th, 7th, 11th, 13th, 17th, all those harmonics are there. If you have m converters of 6 pulse, so this is the equation, and you can see this is the amplitude. So if you have 3 converters of 6 pulse, so m is equal to 3, this m is equal to 3, so you have 18k plus minus 1. So 3 6 pulse converter means 18 pulses, right? 18 pulses, and you will be giving 20-degree phase shift, 60 divided by 3, 20 degree, and you will get 18 pulses, and this will give you what harmonics you will get with 3 6 pulse converters connected in parallel with 20-degree phase shift. It will give you 17. So below 17th harmonics are already eliminated. So this is the advantage of giving the phase shift. So that is why in industry, if you say, okay, this is production line and we can have the same kind of production line for all our equipment, so it will generate a lot of problem if you do it in industry. That's why phase shifting is very important, right? So, and this is the amplitude of harmonics you will get with this formula. Many times we use zigzag connection, delta zigzag. This is delta in the primary. In the secondary, you have a zigzag connection. So what are the zigzag advantage which we have already discussed? That there is no core saturation due to DC component. This is the big advantage of zigzag connections. No zero sequence current in delta in the primary side. Otherwise, if you take DY11 or DY1 or other those type of configuration, on the distribution network side, certainly there is no third harmonics or zero sequence harmonics, but they will circulate in the delta primary side of the transformer, which will heat up the transformer basically. Unnecessarily it is heating up the transformer. But if you have a zigzag connection, then there is no zero sequence current even in delta. They are eliminated. So this is the advantage of having zigzag connection. And then we can have any phase shift adjusting the number of turns in secondary. You see here, like for example, here it is 15-degree phase shift. See, this is the output. So this is from primary side, and in the secondary side you can see 15-degree phase shift. So by adjusting the number of turns here and in this winding, small winding, you can change the angle, whatever angle is required, which harmonic you want to eliminate. You can have 7.5 degree or 15 degree or 20.5 degree, whatever you want, or even you can have one zigzag also like this, okay, which will go like this, okay, so that it will give minus 15-degree phase shift in parallel with this. Double zigzag you can put, sometimes they put double zigzag also. Now zigzag, we have, instead of having zigzag in the secondary, we can have polygon connections. So it is the same transformer, it is just how you connect it. Like the same transformer, either you can connect in delta or you can connect in star Y connections, right? So it is the same thing here. So instead of opening the windings like this, like a star, you can close them like this. So this is a polygon connection. And here also you can have the same thing, like 15-degree phase shift here. Okay, depending on the number of turns in the primary, here, you can adjust the number of turns. And so the only difference, it is closed at delta, zigzag for higher voltage, polygon for lower voltage. But polygon is also very popular in applications. So we can, you may think that it is difficult to analyze this thing, but it is not very difficult to analyze those transformers. Suppose we analyze this polygon transformer, right? In this polygon transformer, you can see on the primary side, you have delta, this winding, and this winding, and this winding. They are on the same leg of the transformer. And the sum of magnetomotive force should be 0 in that leg. So this is how you can write this equation, right? IA is the current here in this winding multiplied by number of turns. So MMF is there, and this is in the opposite direction. I1M current is NL. So number of turns here. So we are talking about ampere turns, like MMF, ampere turns. NL multiplied by IM, and then here you have I3M current in this winding. And this you can say number of turn NS, because it is small winding, or this is large winding, and this is on primary side. So all these three are on the same leg. So sum of all this MMF should be 0. Okay. Now if you see this triangle, this is VNL here, and this is VNS voltage. Sum of these two is this voltage, VLS. This is the output voltage. So if we say this is the phi angle, okay, so you can see here, if you analyze, this is VNS sine 60, this one, and this is VNS cos 60. So if you calculate tangent of phi, so this voltage divided by this voltage, right? So that we have written later, but what we have done, this voltage divided by sine of C. See, this is the trigonometrical function you already know, right? This VNL, this is in front of this. So sine, this VNS divided by sine 60 minus phi, this divided by this angle, this divided by this angle. So this is how this equation, trigonometric function, has been written, and you can find the voltage, VNL, VNS, those things, and then you can write tangent phi. The objective is to find the angle phi. So how you will adjust the angle phi? So that depends on the requirement, what kind of load is there, what harmonics are generated. So depending on, you can do the calculation, which phase difference between the transformer will be helpful to cancel certain harmonics. Accordingly, you calculate phi, and phi you can adjust by the transformation ratio. Okay, so then we have analyzed it here, I1M, so there's some problem. If you see this branch here, I1M is there, and this is I3M, so you can calculate I1. I1 will be I1M minus I3M. Same way you can calculate I2 and I3 using Kirchhoff's current law, and it is easy to write this equation. See, current I1 is equal to I1M minus I3M. Same way I2M minus IM. And then finally you can resolve this equation. And then you see this equation we have already seen. So finally you can calculate IA, IC, and then I1N. This is the current on the primary side of the transformer, IA minus IC. So it is just to give you idea that how you can analyze this transformer. So whenever you have time, you can look into it and try to solve this thing. And then you see this is the equation you can get. Now coming to other topologies, there's so much work is going on in this direction for last more than 20 years. Okay, so it is a very hot topic and people are every year. So here I am not giving you more complex topologies and of multiples which has already been developed. Here I am just giving you the basic idea to so that you might, perhaps some of you might be interested in working in this area. So you see here we have 3 converters connected in series, 3 6-pulse converters. 3 6-pulse converter means how much phase shift? 60 divided by 3, so 20-degree phase shift between the 3. And you have 3, so 18 pulses will be generated. So as you can see here in this line, see it is already so much smooth. If you take only one converter, it will pollute a lot. But now because of the phase shifting, so this is delta, 0 degree here, then this is plus 20 degree and this is minus 20 degree. So this is how you can do the phase shifting using polygon. So delta, double polygon. So delta on the primary side, secondary side another delta, and 2 polygons are there which will give you 18 pulse. So up to 17th harmonic they are already eliminated. So minimum harmonic is 17th in this. So 5, 7, 11, 13 they are already eliminated. And it does not need the interphasing transformer. Now if you see this delta hexagon, primary side delta, and this is the hexagon. So you can have, this is the output 1, 3, 5, see they are connected here, 7, 9, 11, all these output terminals they are connected here, okay, and this 2, 4, 6, 8 they are connected at this point. Okay, so this is full wave midpoint converter, and if you see between 1 and 2, it is 30-degree phase shift because there are how many? 12. 360 divided by 12, so 30-degree phase shift, right? So it is having 30-degree phase shift. But this, so there is already a US patent. This is nothing new. This is old, maybe 20-year-old patent, more than 20-year patent. But you can use this hexagon as auto transformer also. Then you don't need this. Okay, so you can have input here 1, 9, 5. What will happen? 1, 30, 30, 30, 30. 120 degree, right? So you can have input here, you can have input here, and you can have input here, and everywhere else you can have the output. So see, this is the auto transformer. That is also very popular, that type of. So what actually, if you see the multipulse techniques with double winding transformer, and you have option multipulse technique with auto transformers. So what is the advantage of double winding transformer? that it has DC isolation between input and output, right? And what is disadvantage? You have doubling the kVA and other parts. Like if we say, okay, I have a double winding transformer and it is a 10 kVA capacity. So input winding is 10 kVA and output winding also 10 kVA because power has to be transferred. So it is basically you are doubling the kVA, right? So it will increase the size, terminals, boxes, and it will increase the cost and it will decrease the efficiency because more winding wire and more losses are there. But if you have auto transformers, then what is the advantage? For particular phase shifting, design is simpler, reduced kVA. So if we say 10 kVA, it means it is 10 kVA, it is not 20 kVA, right? It is auto transformer, same windings are used. For example, with auto polygon, 30% of double winding transformer, see, this is the advantage. If you have double winding transformer and with like delta polygon or something, or if you have auto polygon, so you will say, so it will be a 30% of double winding transformer. So that much cost you can save. Cost much reduced. This is more compact because now it will be smaller, right, with higher efficiency. And but the disadvantage, there is no DC isolation because same winding you are using for input and output, right? So this is an example of auto connected polygon. Till now we have seen delta polygon or something like this. So that was double winding transformer. But if you want to see auto polygon transformer, so you see this is the input here and this is another input here V2 and this is another input V3. So three input, three phase supply, and then you can have output I2, I1, I2 and I3. So three output. So you can get particular phase shifting with the same transformer. You don't need double winding transformer. You are getting the phase shifting with this. So how to get 5 that we have already seen. You can see this is the phase shifting. This is the, here you have the input and here you have the output. So between input and output, 5 angle phase shift is given, phase shift angle. And it is easy to analyze because you see this winding and this winding, they are on the same leg. Okay, so you can write total MMF on the same leg should be 0. So this is what equation IA NL, if this is NL, IA NL, this is MMF, ampere turn of this winding, and this winding, I think this is NS, small winding, number of turns is small, multiplied by I3 plus IB. So the total MMF you can, because this is in this direction, this is in this direction, so you can write, and then you can write NL you can bring here, and N is equal to NL divided by NS. So you can write this equation for current IA, for this current. Okay. Same way you can write for IB and IC, same type of equation. Then you can see this is IB here. So if you put here, then there is IC here, this equation you can put here, and finally you can find out IA current like this, IC current like this. And I in is equal to I1 minus IC plus IA. If you see this diagram, I in current is here, this is I1 minus IC here, and this is IA. So this is how you can write all those equations. And then you can calculate the phase angle and those things. Another type of transformer is fork connection. This is a fork connection. This is auto fork connection. So you have the input here you have input 1, oh this is I2, this is I1, this is input 1, 2 and 3, I3. These are the 3 input and output is here. See, this is output, this is output and this is output. So between input and output, you have phase shifting 5 degree. Okay, but according to some reviewers, it is less efficient in comparison to auto polygon for same phase shift. KVA is higher than polygon. This is what other people give comments about the transformer. Then we have differential delta. Differential delta is very popular. Okay, so you can see these windings and these windings, they are on the same leg, and this winding and these two winding, they are on the same leg. Okay, so if you write MMF equation, this is IB current multiply by NL, suppose we call it IB NL, and here this is I1 current in this winding, I1 NS, if we say NS number of turns here, I1 NS, but they are in opposite direction, so minus, this is I4 current, I4 NS. So this is what MMF equation you can write. What is the advantage? See the equation. This IB current here, this is proportional to the difference between I1 and I4, differential of these two currents. So it means current IB will be very small in this. So this is IB current is not very large, this is very small because it is the differential between current I1 and I4 because they are on the same leg. So this transformer is very compact and phase shifting you can get here. See, plus 15 degree for this it has been and minus 15 degree. So you can have, so you see these are the inputs. So three phase input. Okay, so here you have 3 phase input like this. Okay, and then you have output. All those I1, I2, I3, they are going to this 1 6 pulse converter, and I4, I5 and I6. This is going to another 6 pulse converter with minus 15 degree phase shift. So total phase shift is 30 degree phase shift. You have between the two, between this and this, you have 30 degree phase shift. And you can connect these two in parallel. So this is what plus is connected to plus, but there is an interphasing transformer between the two. And minus is connected to minus, and there is an interphasing, and this is the output you can connect here. So if you see, this is what we were saying, that for example, I6, where is I6? I6 minus I3, that should be proportional to IA, right? Because this and this, they are on the same leg. So I3 minus I6. This is I3 waveform and this is I6 waveform. Difference of these two, you see, it is going, so see, IA is so small. So it is very compact, very big advantage. Then we have another type of differential delta, right? So that you can connect 3 converters in parallel, same way, and the windings, these, they are on the same leg. So if you are having 3 converters, the minimum phase shifting is required 20 degree, 60 divided by 3, 20 degree. But here we have 40 degree phase shift because 20 degree is the minimum. So some conceptors of the transformer, they said, okay, I can take 40 degree phase shift. So he has taken 40 degree, and this is how he is able to get 18 pulses here. This is another differential fork. Okay, so many different transformer, and this is a hybrid delta, this is auto transformer, and this is another connection. That's why the conceptor is saying, okay, we have the advantage of double winding transformer also, and here we have auto transformer also. So now using these auto transformers or those things, we can have the phase staggering like this. See? Can you see how much money you can save in this thing? Because it is the same thing, like you are using dy1 and dd0. Here you don't have to have any transformer. Directly you are connecting. So 0 degree phase shift is there, right? And here you can have auto polygon with 30 degree phase shift. You can adjust the winding here and here, and you can get 30 degree phase shift. And this is on the top of this is auto transformer, much cheaper. So the cost of this will be 25% of the original which we studied dy1, dd0, the cost of that setup and cost of this setup. This will be 25% of that cost. So this is what engineer has to see, how they can save the money and how they can have good performance. Now this is another double winding. This is although showing double winding, but you can have auto polygon also. Okay, so if you have auto polygon, see the third 6 pulse rectifier, it is directly connected to the supply, 0 degree phase shift, because you are having 3 converters, so 20 degree phase shift. 20 degree, plus 20 degree and minus 20 degree. So this will give you plus 20 degree, this will give you minus 20 degree, and if you are directly connecting to the rectifier, so this is giving you the very cheap option for 18 pulses. Basically you will get 18 pulses, right? 17 up to 17th harmonic already limited. Then this is also popular sometime, that you have for identical loads, and directly you can connect one 6 pulse converter, and since you have 4 converters, so 60 divided by 4, 15 degree phase shift. So each has, this is minus 15, this is 0, this is plus 15, and this is plus 30. So this is how you can have 15 degree phase shift between the converters. And finally it will give you 24 pulses here. So up till 23rd harmonic they are already eliminated. So minimum harmonic is 23rd harmonic. So you can see it will be very good. But sometime what happens that some converter is not working due to some reason, then the performance will not be that good in this, right? We are assuming that all the loads are there all the time. Suppose this is working and this is working, then it is fine, 30 degree phase shift. So even if these two are gone, you still have 30 degree phase shift and you will have 12 pulse performance. But somehow if these two are gone, then it may not give very good performance, because 2 converters and 15 degree phase shift, that will not give very good performance. So there are some advantages, disadvantages, but you can save lot of money in this thing. And then there are other configuration also, but I will. So we have to move on to our other topic, active shunt active power filters. So what we will discuss in this presentation, what are the requirements and applications of shunt active power filters, configurations of shunt active power filters, control of shunt active power filters, sharing of responsibility for harmonic distortion and power quality. So generally we don't find this topic anywhere, but few years back I did a very interesting project in collaboration with Hydro-Quebec, sharing of responsibility. Otherwise it is difficult to do this thing. And then numerical problems and references. So if you see the requirements and applications of shunt active power filters, these are current based power quality problems and in distribution system for which we use shunt active filters. So what are the problems? Problems is that RMS supply current may be high, there might be some low system efficiency because of the increased losses, poor power factor, poor utilization of distribution system, heating of components of distribution system because of the different harmonics, right? And then derating of distribution system. Suppose transformer has lot of harmonics, so you have to derate the transformer, and sometimes you can have only the 50% of capacity. Distortion in voltage waveforms at PCC, interference to communication system, disturbance to nearby consumers. So these problems may arise in a distribution system, and these are current based problems. So for these problems we can use shunt active power filters to improve the power factor, for voltage regulation, for unbalanced current. If there is excessive neutral current, your shunt active power filter will work fine, and then harmonics. So solution is the shunt active power filters for all these problems. So it is nothing new, it is a very mature technology, because you know the 40 years ago this Akagi developed one control technique, instantaneous reactive power theory. So it means that time also they were using, but with the development of IGBT technology and those things, it has picked up so much. So now mature technology for providing harmonic current, compensation of reactive power, load balancing, neutral current, okay. And shunt active power filters, they are also used to regulate terminal voltage, to suppress voltage flicker, to improve voltage balance in three-phase system. So there are so many applications, and so much development has taken place in this technology with varying configuration, advanced control studies. So many, a new PhD student will come, he will develop his own control technique, right? He will modify existing or something, and then, so many control techniques, strategies are being developed. And then solid state devices, so much development has taken place, like gallium nitride, silicon carbide, and so much development is taking place in solid state devices. Improved sensor technology, Hall effect, current and voltage sensor. And then there is a development in microelectronics revolution, microcontrollers and DSPs. So much new products are coming with very good performance and those things. So lot of development is going on with the technology, which is helping to give a push to this active shunt power filters to improve the power quality on distribution systems. If you see the classification of shunt active power filters, you can see, you can classify based on converter type, based on the topology, and based on the number of phases, right? If converter type, you have current source converters, right? And you have voltage source converters. You have, for the topology, you have half bridge topology, you have full bridge topology. Number of phases, you can have single phase 2-wire system, or you can have 3-phase 3-wire system, or you can have 3-phase 4-wire system. Okay, so based on that, the topology will be changing. So if you see the converter based classification, so if you have a current fed type shunt active filter, So you can see current fed, so your IGBT is here and you have to put a diode in the series to counter the inverse voltage, right? And on the DC link you have an inductor, okay? So current source inverters use a constant DC current input to produce a variable AC current output. It uses large inductor for energy storage here and to keep current constant here, IDC. Large inductor may be heavy, noisy and may cost more. So current source inverters are better for high torque applications at low speeds. So this is the application basically for current fed type filters and offer a more stable current output. Now voltage fed type shunt active filter, you have IGBT configuration like this, you have diode in parallel and then you have a capacitor on the DC link, right? So voltage source inverter use a constant DC voltage here input to produce a variable AC voltage. DC link capacitor to maintain constant voltage here. Less losses, high efficiency, smaller size, less noisy, less costly in comparison to current fed type. But current fed type are used for large system and those as we have seen low speed, high torque type. So this is more popular than voltage fed type. They are more popular than current fed type. That is number of applications. So basically it depends what application you are using, right? Topology based classification. See, half bridge topology. So you have a half bridge here, VSC based, single phase. This is single phase shunt active filter. So this is how coupling inductor you are connecting here. And here you have two capacitors and midpoint you have connected here. So this is the half bridge topology. Basically to save some money, it will cost cheaper in comparison to this topology, full bridge topology, because you have another set of IGBTs here and you have one capacitor. So here you are connecting to, because this is again a single phase, okay? So this is how you can have full bridge topology. Supply system based classification, again the same thing. Suppose this is a current source inverter, you can see the diode connected in series with IGBTs and two wire shunt active filter. So it is connected here and you have an inductor on the DC link. Two wire shunt APF voltage source converter. Again, we have seen these things, okay? So this is full bridge type basically, voltage source converter. Three phase, three wire shunt APF. So three phase, this is three phase, three wire. We don't have neutral here. And so we have three phase full converter here. And then on DC link, you have a converter and these are the coupling filters. So this is what the topology you have: three phase, three wire shunt APF with VSC. Three phase, four wire. So now you have neutral also here. You have three phase with neutral current. So sometimes we can use two capacitors and midpoint you can connect it here, the neutral. Though this is cheaper for three phase, four wire topology because neutral is connected to capacitor midpoint. Sometimes triple harmonics may flow through the capacitors. A may require large capacitor sizes. So these sizes may be large because zero sequence current may flow through those capacitors and they may heat up the capacitor. So you may require large capacitor size. So that's why if you use the fourth pole to connect the neutral, so it may look costlier, but it gives very good performance. And then you have 3 H bridge 4 wire shunt APF. You see, this is H bridge, 3 H bridges, and you have a neutral here, and so each phase harmonics are compensated independently by a separate H bridge. Like, see, this is for phase A, this is for phase B, and this is for phase C. For large nonlinear load applications, number of components increase, hence less efficient, because losses, if you are using more components, so losses will be more, and it may be less reliable also. So if you see the principle of operation of this active filters, so main objective, as we have already seen, that current based power quality problem, harmonics, reactive power, unbalanced load like unbalanced current, neutral current, fluctuations. It results in sinusoidal balanced currents in the supply with its DC bus voltage regulation. In general, shunt APF has a voltage source converter connected to DC bus and AC side. Okay, and VSC uses PWM control. Therefore, it requires small ripple filters to mitigate switching ripples. It requires Hall effect voltage and current sensor for feedback signal. Digital signal processing is required. Okay, to implement required control algorithm to generate gating signals. Right, VSC is normally controlled in PWM. This we have done. So other requirement, DC bus capacitor you need AC interacting inductors, injection and isolation, small passive filters. Time domain control, so there are time domain control algorithms, there are frequency domain, so much work, so many algorithms have been developed by a new researcher will come, he has to develop a new control technique to finish the PhDs and get some simulation results and implementation results. So much work is going on in this direction. Okay, so many time domain control algorithms, unit template technique, controller, power balance. So see, so many algorithms, instantaneous reactive power theory, synchronous reference frame theory. So there is no limit. And then still you can have those algorithms. Now, if you see the frequency domain control algorithm, there are so many frequency control domain control algorithm also. So you see, if you see the working of shunt active filters, so this is, you have 3-phase nonlinear load, and you have voltage source converter in shunt, connected in shunt with this. This is the supply source, these are the impedance of phase A, phase B, phase C line, and then because you know this is 3-phase diode, so what you may have perhaps this kind of, suppose you have this kind of current. Okay, so if you don't have this shunt active filter, this current will directly go to the 3-phase source. So what is your objective? Your objective is to have sinusoidal source current. This is the objective, right? So sinusoidal current means you should have sinusoidal current like this here, supplied by the source. Okay, so what is the difference between the two, right? So suppose you have this sinusoidal current of the source, but on the load you have this kind of, so the difference between the two, see, this is the difference between the two. So basically it will be something like this. Okay, something like this. You have to have, so this is the part of current which has to come through this shunt active filter to make the source current sinusoidal. Okay, so There are so many algorithms. The simplest one and which works very good also. This is the unit template or PI controller based control algorithm. So what you do is that you measure the supply voltages. And then using VSA, VSB, VSC, you estimate the voltage amplitude. Okay, so suppose you write VA is equal to Vm sine omega t, VB is equal to Vm sine omega t minus 120 degree, and VC is equal to Vm sine. So this is what is actually you have, right? These voltages. Supposing they are sinusoidal. So this is the thing. So we are assuming that those are sinusoidal voltages in phase A, B, C are provided. So we can write this equation. VSP, okay, so VSP. So what we do is that we measure these voltages divided by Vm, this divided by Vm, this divided by Vm. So these are cancelled out. So you have sine omega t minus 120, sine omega t plus 120. So this is what we are getting USA, USB, USC. You are dividing these voltages by the amplitude of the voltage, estimated amplitude of the voltage, which will give you sine omega t minus 120, sine omega t plus 120. So this is what the unit vector you are having, unit template. Now you measure the DC link voltage, and this is the desired DC link voltage, and then using the PI controller you calculate estimate the amplitude of the supply current, and that is the amplitude is multiplied by these three unit vectors, and finally you are getting the reference for source phase A voltage current, reference for source current for phase B, reference for source current of phase C. Okay, so this is how, you see, this is what we are doing using this one. Then there is another algorithm which we developed many years ago, but this is what you have to see when you are, what is actually classical theory. What happens is that either you do voltage regulation theoretically, either you voltage regulation or power factor correction. The two cannot be 100% good. So there is a trade-off between the two. If you are doing the voltage regulation, then you are required to give some leading current, then only you can do the voltage regulation. So see, here you see, suppose this is the load voltage and this is the line current. So drop in the resistance and drop in the reactance source current. So this will give you drop. So basically this is the source voltage. So you see, this is the voltage regulation is not there. This is without voltage, without shunt active power filter, your voltage regulation, this is the load voltage much lesser than the source voltage. So what we are doing using the shunt active filter, see, this is the load voltage, this is the load current. Okay, so we give this current by the compensator of shunt active filter. So shunt active current plus load current, it will become the source current like this. So source current parallel of this, you have drop in the resistance, perpendicular to this drop in the reactance. So you are getting the source voltage. So it means this, if you draw the circle, see the source voltage and load voltage, they are same amplitude, and this is what you are getting the voltage regulation. But at the same time, your power factor, if you see the angle between Vs and Is, power factor is leading, not unity power factor. Okay, so this is the trade-off. You have to see how much power factor improvement you want, how much voltage regulation you want, and accordingly you can put the weight. So this is what we can do here. We are measuring VDC. This is the reference of DC link voltage, and we estimate average DC bus voltage amplitude of in phase component of the reference. So this is what is this? This is the estimate of the amplitude of in phase component. See D, in phase component of the source voltage. And you are measuring three voltages, VSA, VSB, VSC, and you calculate the amplitude like we have done earlier also, and you calculate in phase unit current vector, these. Then you multiply this current by this will give you the reference in phase source current references. But if you calculate the quadrature of this and you multiply with this, because you have this amplitude of the source voltage estimated, and this is the required one, and it will computation of the amplitude of the quadrature component of reference supply current using. So this is the quadrature amplitude of the quadrature current multiplied by the quadrature current vector, which will give you the reference of the source quadrature voltage current for phase A, phase B, phase C, and these two together it will give you the reference of the source current. So this is what is the basic thing. Now there are so many algorithms. Okay, so everybody saying, oh, this is good, so whatever works is good. Okay, so this is instantaneous reactive power theory. So many people are using it since 1983 when it was developed by Professor Akagi. Okay, so what is there? You measure VSA, VSB, VSC, you do the Clark's transformation, ABC to alpha beta transformation, V alpha, V beta, you measure three load currents, ABC to alpha beta transformation, I alpha, I beta, and then you calculate using this equation. So this is what the work of Professor Akagi. He calculated load power, active power and reactive power using this equation, and then PL, QL, and finally instantaneous active power and instantaneous reactive power by adding some losses here and some voltage regulation thing, and finally using this equation you are calculating I alpha reference, I beta reference, and then you can do inverse Clark's transformation, alpha beta to ABC, and you are getting three reference source current. So this is what is the basic idea of instantaneous reactive power theory. Then there is another very interesting synchronous reference frame theory was developed. This is still older. This was perhaps developed in 70s. Okay, so but application is still there, right? So what is there? You are having load currents, and you are having ABC to basically Park's transformation, ABC to DQ0, ILD, ILQ, and then you are measuring VSA, VSB, VSC, and using three-phase lock loop. In MATLAB, you will find this block. Okay, so to calculate cos theta sin theta term. So using this cos theta sin theta term, you can use it here to calculate ILD, ILQ, and then low pass filter, DC component of ID current and DC component of IQ current, and then you are adding some current losses, so ID reference, and here you are adding for voltage regulation Q quadrature current, IQ reference, and then DQ to ABC transformation, and you are calculating this reference source currents. So basically, as you have seen, the objective is to calculate the reference of the source current. There was some algorithm I saw, they calculate reference of the compensating currents. But that is more involving, more time consuming, so they are generally not preferred. So instead of calculating the reference of compensating current, we calculate reference of the supply current. That gives better performance. So if you compare these two popular things, everything is working fine. So one student will work on this SRF, another will work on instantaneous reactive theory, PQ theory we call it, and everybody claimed that they are working fine. So everything is working fine. Okay, but what is theoretically you can say?
Sometimes I feel that these two theories are sufficient for ourselves.
Yeah, so see, synchronous reference frame theory is more robust theoretically, for saying theoretically, for shunt active filter, especially under unbalanced conditions. If the voltage is, supply voltage is unbalanced, then, right? While the instantaneous reactive power theory is computationally simpler, but performs poorly with unbalanced supply voltage. Okay, this is what actually people say. SRF uses transformation paths and inverse transformation, which increases its complexity, whereas instantaneous reactive power theory avoids this, but requires balanced and sinusoidal source voltage for effective performance. But now so many variants are coming, so researchers, they try to modify SRF also and instantaneous reactive power theory, and they say, okay, it's working fine. And most of the cases, really it works fine, nothing to worry about. Now, if you see the performance of 3-wire APF active power filter at non-linear load for harmonic elimination. See, this is the supply voltage, this is the supply current, load current for phase A, load current for phase B, load current for phase C. Can you see it? And these are the active filter currents for phase A, phase B and phase C. And this is the DC link voltage. So see, if you see the load, phase B load, phase A load, phase C load, and if you see the compensator currents here for phase A, for phase B and for C, so it means they are compensating for this non-linear load so that the source current is sinusoidal constant. So this is what actually basically, as I discussed in the beginning, that this is what is the objective, to have the sinusoidal source current even if whatever load is there. So your compensator should be able to do it. This is what it is doing now, right? Now in this period you can see load current, load at phase A is disconnected. So you have currents in phase B, load B and load C. So still the current which is coming out from the source, it is reduced because 1/3 load is reduced. So still it is sinusoidal and harmonic free, right? This is the what we are, and you can see the three phases of the same shunt filter, they are providing, it is providing different current to compensate this basically, because there is no current, so it is almost sinusoidal here to compensate it. So this is, and if you see this is the voltage of phase A, this is the source current of phase A, and this is the load current of phase A. So if you see the THD in voltage of phase A, it is 5.96 THD. and source current THD is 1.6, much less than 5%. And load current THD, it is more than 23% THD. So it means your active shunt active filter is working fine and harmonics are being removed. If you have 4-wire APF with neutral, okay, so here you can see this is the source voltage, source current, and this is the current in the neutral wire of the source. This is load current in phase A, load current in phase B, load current in phase C, and this is the neutral load current, this one. And these are shunt filter current phase A, phase B, phase C. So here you can see this is the load for phase A, B, C, and these are the shunt active filter current. So they are working in such a fashion that your source current is perfectly sinusoidal and of the constant amplitude. But now phase A load is disconnected. So you see the compensator current for phase A, B and C, they are still functioning in such a way that the source current, although is reduced because this load A is reduced, so still it is sinusoidal. Okay, and at the same time you should see the neutral current for load A, for line neutral line neutral current. Okay, and but here you see the source current, source neutral current, which is 0. It means load neutral current is there, but it is not appearing towards the source. Okay, because this current has been compensated by this. Now let us see, this is again the THD and those things. Oh, these are the experimental results for APF under, so this is VSA phase A source voltage, and this is, oh, I think the student has put the same source current, although it is written ISA, ISB, ISC, but still you see, and then this is the source voltage and this is the load current, right, load current, and this is the source voltage and this is the shunt compensator current. Okay, and that's why your source, and this is to show harmonic spectra of ISA. THD here is 3.9 and this is load current THD 26% THD, and this is VSA 6.3 in VSA. Dynamic performance of APF during, I think we should hurry up, there are so many results here. Just to the, like phase A load is removed, compensator was working fine, so that is why it's sinusoidal, and here current is reduced, but it is equally distributed. Load A, load of, but so it is becomes load, but it is equally distributed in source. This is what actually you see it in all the source current. This is what basically. Then there are some thing implementation. it is just to show here. See, this is the source 0, while the load, you see, you have the, because your load phase C is like this. Okay, so this load neutral current, but consider shunt active filter is generating current in such a way, you see, opposite of this, it is to cancel out this. Source neutral current is null. Load neutral current is cancelled by the shunt active neutral current. Yeah, this is what actually I wanted to, although this is not that interesting for other applications, but sharing of responsibility for harmonic distortion and power quality. So this is what we did project. Although I did it 20 years ago, I engaged my postdoc and PhD student in this. And there was one researcher at IREC. IREC is the Research Institute of Hydro-Quebec. It's a very big, 500 researchers or PhDs are working in that institute. So there was one very good researcher, Professor K. Srinivasan. He was working on this problem, that your PCC voltage is all polluted, right? A lot of distortion in the voltage. And all the clients connected to PCC, they are also polluting the network. So how will you decide who has done how much pollution? This is a big question. Because another client may say, no, this is not my pollution, I have not done this. Another client may say, this is not my responsibility. How to share the responsibility of harmonic distortion and power quality. So this was, so he did theoretical work, but he did not know how to implement it. So that's why he came to me, okay, this is my theory, how we will implement it. So that's why we did this project, okay, to help him out.